So, okay, let us get started here. Today we are going to talk about Minix memory management, but before I do that, I had a couple of things to announce or re-announce. First one is the midterm exam, as I have already mentioned before and posted on Piazza. It is going to be on March 10th. It is going to be an evening exam, 7 p.m. Where do you go for it? Okay, computer science, but do not come here. You will not get an exam here. Okay, so go to the CS building, room 142. That's the larger of the two classrooms there. Okay, so that's something that you should keep in mind. The other thing is there is a lab due next week. Okay, I hope all of you have started. If you have not, please do immediately because it is going to take some time and effort. Do not wait until the last minute. Okay. And just to give everyone a sense of what is coming after this lab is done, there will be two more labs, of which one is a really straightforward lab and a project. Okay. So, we will do the midterm, and then just before you go out for spring break, the third lab will come out. It is going to be on memory management. Some of what we talked about last time and today will be concepts that you should know for memory management. Okay. And then we will have one more mini lab really after that, which is going to be on Docker and OS virtualization. Okay. And then the project itself is going to be really like a longer lab, but we will call it a project. That is kind of the capstone thing you do for the course. That is going to be on device drivers and file systems. Okay. So, the idea is you implement a small device driver and then you implement a user space file system. Okay. So, that is what so essentially there are really two labs, one a regular lab and one a little bit longer lab, which we call the project, and the Docker lab is really a very straightforward lab. It should not really take that much time, but it gives you some exposure to Linux. It is the only Linux lab in the course, right, because everything else is Minix based. So, that is going to be a Linux lab. It is going to make you do some interesting stuff with Docker and OS virtualization. Okay. Is that clear what is coming? So, I just wanted to give the big picture here because there have been some questions on Piazza asking about projects and other labs. All right. Okay. So, let us get started with Minix memory management. So, if you remember last time I did a refresher on memory management. We went through several different memory management schemes and so on. Okay. So, we will continue that discussion, but make it more Minix specific. Okay. Just so that all of you know, we should not have laptops open during class. Okay. All right. So, now as far as Minix is concerned, the memory management and process management are intricately tied. Okay. And the reason for this is memory is allocated to processes. Okay. So, when you start a process, you have to allocate memory for it. When you terminate a process, you allocate memory for it and so on. Okay. So, the functionality that you see in terms of the source tree and so on, you will see that process management and memory management is closely tied to one another, and the functionality has also evolved over time. Okay. So, if I ask what does Minix do for memory management, there is no one answer because it depends on the version. Okay. And I will show you how things have evolved. So, earlier version used simpler memory management schemes. More recent versions have actually made them more sophisticated. So, I am going to talk a little bit about both. So, you get a sense of not just the evolution, but also how things can be done if you make more simplifying assumptions about how memory needs to be handled versus how you should handle memory if you have all of the features we talked about last time, like segmentation and paging and virtual memory and so on. Okay. So, let us talk about the simpler variants of memory management. So, Pre-3.1 okay, in Minix. Yes, I think 3.1 is around when they started adding lot more newer functionality. So, the older versions of Minix made lots of simplifying assumptions about how memory should be handled. Okay. So, first thing is there was only one user space server, which was the process manager that did both. Right. So, if you look at Pre 3.1, you have to look at the PM code to see that it is handling not only processes, but also memory allocated to the processes. There was no separate memory manager. Okay. Everything was essentially in the process manager. Okay. Now, what was the scheme that they assumed? They assumed that a process is a collection of segments. So, it was essentially using the segmentation approach that I presented last time. So, every process was assumed to have a stack segment, a text segment, a heap segment, few other segments, and that is basically what they assume. Okay. Furthermore, they assume that each segment was contiguously laid out in memory. I am going to draw a picture here, so it is all clear. Okay. So, you have, so this is RAM. So, let us say you have a process. Okay, process has multiple segments. So, we will say this is the text segment of the process, this is the stack, this is the heap. Right. So, we will assume, and that is just one process, we assume it has 3 segments, each segment is contiguously laid out, okay, but the segments themselves do not need to be adjacent to one another, they could be anywhere in RAM. Okay. That is the assumption that was made. Okay. So, essentially if you look at this picture, you will see that once there are multiple processes resident, your RAM essentially looks like a collection of holes with an allocated segment. So, it is a sequence of holes followed by segment, hole, segment, and so on. Okay. So, all of the stuff we talked about that relates to contiguous memory allocation, okay, that is basically what this approach used as far as allocating memory was concerned. Okay. All of the processes in this case are in physical memory, in RAM. There is no virtual memory here. Okay, there is no demand paging in earlier versions of Minix. Okay, that is the thing you want to keep in mind. Okay, no paging, no virtual memory, and so on. Okay. Now, the reason they did this is if you want to implement more sophisticated memory management techniques, we will see soon that you actually need hardware support for it. You need to assume a modern processor, for example, that has paging hardware, that has TLBs and so on. So, if your CPU does not support this feature, fundamentally you cannot implement those approaches in your operating system. Okay. So, Minix, when it was designed for older CPUs, it was designed for more embedded processors, which typically do not have support for paging, which is why they went with a segmentation approach. So, if you take any low end CPU, essentially you have to make this assumption that the entire process is resident, maybe the process is contiguously laid out, you cannot assume paging and things of that sort. Okay, so early versions of things like Raspberry Pi or Arduino, you would actually have to make these kinds of assumptions if you want to build an OS for it. Okay. Now, as hardware has evolved, so has Minix. So, modern versions of Minix, which is really post 3.2, including what we use this class, which is 3.2.1, essentially assumes more sophisticated memory management, anything that a more general purpose OS also supports. Okay. So, there is support for paging, there is support for demand paging, virtual memory, and things of that sort. Okay. Now, to do this, they have made some changes in the code. So, you will see that around 3.2, they started introducing the notion of a virtual memory manager. So, there is now a VM server that is separate from the process manager. All the memory management code has been taken out of the process manager and put in its own server that is responsible for memory management. Okay, so, now you will see that the code is split. So, the VM is different from the PM. It introduced support for paging, virtual memory, and so on. Okay. Now, in this case also they assume that processes are a collection of segments and that segments are contiguously laid out, but they are not laid out contiguously in physical memory, they are laid out contiguously in virtual memory. Okay. So, the picture you want to keep in mind is you have RAM here. Okay. So, independent of RAM, you have this abstraction of virtual memory. Okay, notice that I made it bigger than physical memory because that is what you want to assume, that virtual memory is effectively infinite. It is a large memory region, and what you assume is processes are first laid out in virtual memory. Okay. So, you will basically have segments here. So, let us say this is process 1, it will have a text segment, then you might have a heap, you might have stack, and so on. Then your process 2, same thing. Okay. So, we will have text, heap, stack, and so on and so forth. Okay. So, you are assuming that in virtual memory processes are still contiguously laid out, but that is no longer the picture for physical memory, okay, because physical memory is now paged. Okay. So, here you are going to have a collection of pages, okay, and some subset of these pages are now going to be mapped to physical memory. So, now the entire segment is no longer in physical memory, only parts of it are going to be in physical memory, and they are going to be demand paged in, and virtual memory is going to be on disk, okay, very similar to what any modern OS would do and what we discussed last time. Okay. So, more modern versions of Minix will essentially use segmented paging, okay, because I introduced both this notion of segments and I have introduced paging. So, essentially you are going to use segmented paging and you are going to use virtual memory to do all of this. Okay. Is that clear? Okay. So, segments are paged. Okay, so, now with that picture in mind, we are going to now go and look at a whole bunch of these concepts all over again, but with more of a Minix orientation. Okay, we will see what does Minix do to implement various concepts. Last time I just introduced many of these concepts in a more generic way. Okay, so essentially we are going to discuss the VM, the virtual memory manager, in some detail, and we will discuss parts of the process manager as well, because it is still doing some things to allocate memory and whatnot. Okay. So, there is now a nice document that you can go to the Minix 3 wiki, and if you look under developer docs, you will see that there is a description of the virtual memory manager in it. Some of the contents of the lecture are taken from there, but it is a good document to read to understand what is going on. Okay. As far as the book is concerned, if you actually go and read about this in the book which is in chapter 4, it is assuming the older version of memory management. It does not actually have of a VM in it. So, the book is out of what you in this class, that is as far as memory management is concerned. Okay. So, do not use the book to actually get a feel for what Minix does as far as this course is concerned, because the two do not match up. Okay. The book talks about an older version where you did not actually have paging and things of that sort in Minix, but the current version of Minix does have all of those things. Okay. So, here is an example of an interaction between the process manager and the virtual memory manager. Okay. So, let us say you create a new process, you are going to call fork. Okay. So, the fork that is going to be handled by the process manager. Okay, to implement fork. So, that is a call tree, and maybe I do not know if it is readable in the back, but I have those slides, so you can go back and look at it. So, what you will see essentially is your parent process is called forks. It comes to the process manager. Process manager tells the virtual memory manager saying, I allocate some memory for a new process. Okay. What is the virtual memory manager going to do? It is going to look in virtual memory. Okay. Find some holes that are big enough to accommodate the new segments, which are the text segment, the heap segment, or whatever the segments are. Okay. So, you are essentially going to go and look for, scan the holes and find a region of memory that can hold that process. That is going to be done essentially when you do fork and set address space, and then you tell the kernel saying, okay, this is a new virtual address space for this process. Okay. And then you will come back and then you will actually do a fork to create the new process ID and things of that sort, and then you are going to return back to that process. Okay. So, you will see that process creation is intimately tied to how memory gets allocated. Okay. So, that tells you that this was the reason in early versions all of the code that the VM has now was actually in the process manager, but now they have separated it out, and so you get all of this functionality in two different processes. Okay. So, let us go back to the VM server and try to understand what kinds of concepts it is. Okay. So, first thing is it will have architecture dependent code or hardware dependent code and hardware independent code. Okay. Unlike things like processes, which were really hardware independent, there was really no hardware dependency, but when you come to memory management, you see that the code actually has, you will see for 3x86 ARM architectures and whatever hardware you need to support, you will need code for it. Okay. Now, you say, why do we need hardware dependent code? The reason is lot of the memory management, the low level memory management details is actually going to be dependent on what the CPU does as far as paging is concerned and how segmentation works and so on. That is very much hardware dependent. So, there are some parts of the memory manager that is going to be very specific to a particular processor that your OS is supporting. Right. Once you have done that, the rest of it is independent. Okay, what technique you use to decide is this first fit, best fit, all of that is not dependent on the hardware. That is hardware independent. But as far as setting up the process, the page tables and all of those other things are concerned, there will be hardware dependencies in here. Okay. So, this is probably the first time we are actually looking at a component of the OS where you will see there is code that is actually going to be dependent on what processor the OS is going to run. Okay. In this case, we are going to assume an Intel x86 processor. We are not going to look at other processors as far as the lecture is concerned, because your virtual box effectively emulates an x86 processor, and that is all you need to know as far as the class is concerned. But you should also know that there is code in there to make Minix run on other CPUs, not just x86 CPUs. Is that clear? Okay. All right. So, there's architecture dependent and independent code. Now, there are some data structures that you want to keep in mind, and what Minix uses is this collection, or not collection, but terminology called regions, which is essentially a contiguous section of memory. So, there are virtual regions which stand for virtual chunks of memory. There are physical regions which are essentially referring to physical pages in memory. Okay. And memory allocation is done through those data structures. Give me a chunk of free memory in virtual address space, then you will essentially use the first of those data structures, or say give me some number of physical pages, you are going to essentially use the second data structure and look in RAM. Okay. So, you have to distinguish between what is happening in virtual memory and what is happening in physical memory, because the two are different. In this case, you are essentially going to look at contiguous chunks. Here, you are going to look at pages, because this is page and that is assumed to be segmented. Okay. Now, there is another data structure that you want to keep in mind, and that has to do with a disk cache. Okay. So, the memory manager also holds the disk cache, okay, and I am going to come back to why you need a disk cache in the memory manager shortly. Okay. But there is a disk cache, it holds blocks of the data that you read from the disk, and it keeps it in the memory manager, and we will look at why that is needed in just a little bit. Okay. So, these are three data structures you want to keep in mind. Okay. Now, let us take a look at a few more details of the virtual memory manager that shows you how the code is laid out, how the interactions work and so on. Okay. So, at a very high level, there is essentially calls to the VM. They either come from user space, okay, to allocate memory for heaps and so on, or they come from the process manager when you are doing a fork or an exit and things of that sort, or you might get occasionally calls from the kernel. Okay. Now, regardless of where the call comes in, the handling is always done in the following way. In the main.c, you are going to receive that call. Okay. You are basically the main loop that is basically looking to hear from any of those other components. And then once you have received a call for allocating memory, deallocating memory and so on, you are essentially going to go into the code of the VM and call specific files or specific functions, which could be memory mapping or caching or page faults and so on, and have them do certain tasks. And then you got to do some bookkeeping, which is update data structures and return. Okay. So, every memory management calls involves taking some actions and updating some data structures like page tables or the caches and things of that sort, okay, at a very high level. Okay. And so, here in this picture you have an example of mmap, which is memory mapping. Okay. I do not know if any of you know what mmap is. It is a generic concept in operating systems, nothing to do with Minix. Anyone know, remember what mmap does? Yes. It gives you a pointer to a block of memory. It does, but that is not quite what it does. That would, even malloc would do that. Mmap also gives you a pointer, but it does something more than that before it gives you a pointer. Yes, James.
Doesn't it track that pointer of memory is accessible to a certain process, so it doesn't give it to another process?
Okay. So, it does track memory also, but there is something it does before that which the word map should tell you. Okay, mmap stands for memory map. Okay. Memory mapping is used in it's a generic concept in Unix that is used for variety of things. One thing you can do with mmap is take a file and mmap that file. Okay, so what that is going to do is essentially create a memory abstraction for that file. So let me show you an example. So let's say you have a file on disk. Okay, so you have a file here which is in green, that's your RAM. Okay. If you mmap this file, essentially it's going to allocate some memory and map a certain region of memory to that file. So now you can read or write to that memory region as if it's just an array of bytes, and then every time you read or write to it, those requests are actually going to be satisfied internally by making disk IO to this file that's mapped there. So it effectively looks like this file is and reading or writing to that memory region triggers disk IO. So, you are not explicitly reading or writing to disk, you are reading or writing to memory regions, and the OS is reading to that or writing from that disk for you. Okay. That is what an mmap call does. Okay. It can do other things, but this is it's a memory mapped file. Okay. In any case, I think so here you have mmap, and essentially it is going to go and allocate memory to do that. Okay. So, and then do a few other things as well. Okay. Any other question? Yes, please.
Is it like for efficiency that whenever you make any changes for the file, it will happen to memory, and then at the end of once you're done with it, it will come down to this?
Right. So, question is why do you need mmap? It is again not a Minix specific question. So, this there are programs that will use mmaps rather than explicit disk IO because it is just a simpler abstraction. The file just looks like an array of bytes in RAM. You can just read or write to it as if it was all there. The OS can even cache portions of it for you in memory so that it can be fast, and then you can just not have to worry about actual disk IO. Okay. That is one way to do one reason to do it. And memory mapping is also sometimes used to share memory regions across processes and so on after you do this mapping. You can also actually map regions of one process into another process's address space. It does not have to be a file. Okay. You can essentially take one process's memory and map it into another. So, it can be also used to share memory and so on. Yes. Does memory mapped IO use mmap call? Yes, I think mmap is essentially doing memory mapped IO. Any other questions? Okay. So, as far as our discussion of VM is concerned, mmap is not really of concern to us. I just wanted you to know what that mmap call does there. Okay, and that is essentially what it's doing. But from our perspective, really what is happening here is you are the work of the memory manager is essentially implemented in several functions that are part of mmap.c or pagefault.c, which we are going to come to region.c, which is actually allocating entire regions, holes and things of that sort. Okay. So, that is the structure you want to keep in mind really. Okay. So, now let us start because Minix, the new version of Minix essentially uses paging and demand specifically demand paging. You are going to have scenarios when the process tries to access a page or some memory address and the page is not in memory. So, you are going to get a page fault. Okay, that is what a page fault means. You have to access a memory address and that location is not actually that part of that is not resident in RAM, it is actually on disk and you got to fetch it. Okay. And here is code that shows you how this can be handled. Okay. To understand this, we should now try to distinguish between two types of page faults, which unless you have gone really deep into an OS, you probably have not been told. Okay. There are page faults, or there is something called anonymous page faults, and there are page faults on files. Okay. I am going to talk about anonymous page faults first, and then I am going to talk about page faults on files. Okay. And then I will try to also answer why there are these two kinds of page faults. So, anonymous page faults are the usual kinds of page faults where you have something in virtual memory, the process try to access an address there, it is not present in RAM. So, you got to go and fetch that page in memory and bring it to memory. Okay. So, this process is referred to as handling anonymous page faults. Okay. So, it is the usual thing that you will see in that picture again, that you essentially have a page fault message. It comes to the virtual memory manager, that is handled in page fault.c. It is going to go and ask for an actual frame, saying allocate a frame where this page can be fetched from disk. So, you have to go and throw something out. This is where you are going to have page replacement come in. Okay, remember I said you can use things like LRU and whatnot. Okay. So, you are going to evict a page, okay, and then once you evict a page, you are going to essentially go and read that page, okay, and then you will see that the page has come to memory, and then you are done with handling that page fault. Okay. So, handling a page fault requires you to decide which page to evict, okay, and then you go and get the page from disk and put it there. Okay. Typically, virtual memory, okay, so all of this what I have shown here is stored on disk in a special partition. Okay, it is not stored on the file system partition, it is stored on a special partition. Does anyone know what that is called? Okay, it is called a swap partition on disk. So, typically you will not see that partition. What you see on disk is your file system. You will see all your files, but there is a region of your disk that is actually reserved for storing all of the virtual memory data. All the processes that are active, they are all stored, and you do not want users to see this, because if they go and overwrite it, some process will crash, because that is data for a process that is actually stored on disk. Okay. So, that is an additional detail you should know. So, all of this is actually reading or writing to a swap partition. Okay. So, when you do a page fault on a swap partition, that is called anonymous page fault. That is what we just discussed. Okay. If you do a page fault on the file system, that is called handling a page fault on a file map region, or handling a page fault on the file system. Okay. So, you can have page faults on the to parts of the process that trigger reading or writing from the file system. Okay. Let us ask, why is that even going to happen? Why do you think that if a process actually causes a page fault, that is going to require you to read or write from a file system? Why is it not adequate for you to read or write from the swap partition? Yes. Okay, maybe it's the first time you access the page. You could, but why was that page not in virtual memory here? Okay, and where is it? Okay, code of the program. That's the important part. Yes, you had something to say. Yes. It's the same cost, but the question is, why is there stuff on the file system for that belongs to this process as opposed to virtual address space? Okay, and this is where as I said earlier, this is where you actually have to think about what the page fault is doing for us and what is trying to fetch. Remember that a process has at least 3 segments. There is a text segment, there is a heap segment, and there is a stack segment. Okay. The heap and stack are data segments. Okay. They store data for the process. Those segments are actually always kept in virtual memory on the swap partition. Okay. But the text segment, you do not necessarily have to keep in virtual memory. Okay. I drew a picture here that showed that it is actually in the swap partition. It need not be. It could actually be swapped directly of the file system if that file is actually an executable. So, if you create an executable, you compile a C program, it creates an executable, that is essentially a text segment. It has machine code already. Okay. So, you can directly swap off that file rather than copying that file here and making a text segment here, because that just wasted, you just wasted some space, because all of that is exactly the text segment. Okay. So, what many OSs do as an optimization is, if you are executing a binary, this is not going to work if you are executing code, which is really an interpreter, right. So, that does not work, but if you have a compiled binary, okay, that compiled binary is essentially the text segment of your process. So, in this case, when you start that process, you are not going to load that process in RAM, neither are you going to copy that process in virtual memory and create a text segment. You are directly going to swap off the file that is stored on disk. Okay. That way, you are just optimizing for some disk space and not creating multiple copies. Okay. So, now if you have a standard page fault where I am just executing something in that process and I just hit an instruction and that page is not in memory, I got to go fetch it from disk. Okay. But where is it on disk? It is on the file system, because I am paging directly of that binary file, I am not paging of the swap partition. Is that clear? Okay. So, this has a few implications. First of all, the file system is now involved in paging. Okay. You are paging directly of the file system as well, not just the swap partition. So, there is some paging activity that is going to go to the file system as well, if your text segments are actually stored on the file system as an optimization. You need not have done that. You could have simply copied that entire file into the swap partition and allocated it a text segment. That would have been fine as well, but as an optimization, you decided not to do this. Okay. So, that is the first thing. So, there is going to be page faults on the swap partition and the file system. Okay. Yes, question.
The optimization is not replicating or not using up like twice the amount of storage on the disk.
That is correct. The optimization is just don't, A, you have to make a copy, which means it is going to cost you some, and second, you are going to use more space than you need to, because all of that data is already on disk. Why make a second copy? That is the, so goes the thinking. Okay. Now, the second implication is, if you have an executing process, okay, that has stored its text segment or that swapping off the file as its text segment, if you delete that file while the process is executing, the process is going to crash. And you can actually try this if you want. On Minix, you can execute a process and write a C program, okay, compile it, start it, and while it is running, if you delete the file, your process will actually crash. Okay, because now it cannot page in any more pages, unless all of the pages are already in memory. If it adds another page fault, it is actually going to crash at that point. Okay. There are some OSs, I do not know if Minix does this, but I know there are some OSs that are smart enough that when you delete a file, if you are paging of that file, it will actually make it invisible in the file system, but it will not release the data of those files. It will continue to page off it, and only when the process terminates will it release the blocks. Okay. But those optimizations are extra optimizations you got to put in the file system, because if you delete a file, you assume that the data is gone. But some OSs will be smart enough to know that the user does not want this data, but the OS still needs it to swap off it for the process. Is that clear? Okay. So, now let us come back to this picture. So, this is the other kind of page fault where you are actually servicing the page fault from the file system, and you will see that in this case you have a VFS in the loop, because you got to go to the VFS is the file server in a file server process. So, you are going to handle your page faults, go to the file server saying please bring this file, okay, to memory and so on. And this is where the disk cache is going to come in. If you remember, I said earlier there is a data structure that is called a disk cache. Okay. The disk cache in this case is simply storing blocks of the text segment in memory. Okay. So, you will see here, if you read this carefully, you first essentially go and look for the file cache, and if it is not there, you tell the VFS saying go bring that page in and put it in the cache, and then you restart that entire call tree, and then you this time you have a cache it. So, you essentially read that page and then execute it from it. Okay. So, there the disk block cache is in the virtual memory manager for this reason, because you are paging text segments on the file system, and you want to keep some of them in memory in a OS cache. Okay. So, these are all additional details that are specific either to Minix or any other OS as well, that you have to keep in mind. Any questions on this? Okay. All right. So, now I am going to switch to some other details, some data structures that you need to know about and so on. Okay, the first thing is, as I said, you have to track which regions of memory are allocated and which regions are in unallocated. Okay. In early versions of Minix, this was being done for physical memory. In later versions of Minix, you still have to do this, but for virtual memory, okay, because physical memory in that case is paged. Okay. So, the question is, how are you going to track what is in use or not? There are two data structures you can use for this, either a bitmap or a linked list. Okay. A bitmap essentially keeps a bit for every chunk of memory, and it's marked 0 or 1 depending on whether it's in use or not. Okay. Minix has this notion of clicks. Okay. I don't know what that word means, but it just essentially stands for a chunk of memory. They don't call it a page, they call it a click. Okay. So essentially a 1 bit per click, which you can just think is 1 bit per chunk of memory that looks like a page, and you can essentially have that bitmap shown there. You will see that there is a 1 means it's in use, and 0 essentially means it's not in use. So there's 1 bit per click or 1 bit per page. Okay. That's one way to track for an entire region of memory, whether it's physical or virtual, how many which clicks or pages are in use or not in use. Okay. The other data structure is you can use a linked list. Okay. This is the second data structure shown here, where you have you can say the P stands for a process, and then you say the process has 5 pages, then you have a whole, and there's a process, whole, and so on and so on. So that's basically saying whole segment, allocated segment, whole, allocated segment, whole, allocated segment, and so on. So it's just a linked list of all of these regions of memory. Okay. Each is contiguous. Is that clear? Okay. So these are data structures that you will typically see. Okay. Now, you will see in Minix there's still code for things like first fit and best fit and so on, that will scan through that linked list looking for a chunk that is large enough for a new segment or a new process. Okay. For early versions of Minix, this was done for physical memory. Now you still have to do this for virtual memory, okay, to allocate memory to a new process. Okay. So now with that in mind, let's look at a little more hardware details to understand how paging works. Okay. So first thing you want to know about paging is what the hardware needs to support. So typically your CPU needs a component called a MMU for you to support paging at all. MMU stands for Memory Management Unit. Okay. Typically an MMU will have, there's a picture I'll show that's a little better than this. Typically you'll see that there are 2 green boxes there. MMU will have an associated TLB, okay, which is going to essentially help you cache some parts of the page table and things of that sort. Okay. So when once Intel introduced MMU in its hardware, you could implement paging more efficiently. Okay. Otherwise, if you remember what I had said, paging will cause a factor of 2 slowdown, because the page table is in memory, and then if you try to access that data structure to do address translation, you are going to have a slowdown. So you need hardware support to speed this up. All of that is implemented in your MMU, all the logic to do translation and so on. And as a picture to show you how this works. So here's an example. Okay, so this is an MMU that has entry for a page table of size 16. This is your virtual address in terms of bits. Okay, you look at the k more significant bits, that tells you the page number. Okay, so you essentially, in this case it's page number 2 because it's 001 binary 2. Okay. Then you basically look up the second entry. So that tells you the frame number, that's 110. So you take 110 and you substitute this with 110, and then you basically get a physical address. Okay. So that's essentially has to be all done in hardware for you to make it efficient. Okay. And you will use the TLB to do all of that as well for you. Okay. All right. Now, another concept that modern CPUs will provide is support for multi-level page tables. Okay. Does anyone know what a multi-level page table is? Yes.
It's like another level of abstraction. It's like one page table where there's multiple page tables that have, and like the lower level of page tables has the physical memory, whereas the upper level just references more page tables.
Okay. So there are 2 levels of page table. That's, you can see that there. Okay. Why would you need a multi-level page table to begin with? Let's ask that question first. Yes. Okay. Page tables could be too large. So let's assume that you have a single level page table. Okay. If a page table and it's just a table, right? It's just a hash table or an array essentially. So if you had one level of page tables, and when you start a process, you don't know how large it is going to get, right? Because you don't know if the process is going to do a lot of mallocs and is going to become large, or where it's going to stay small. So your page table has to be pre-allocated when you start the process. Okay. So, if you do not know how large the process is going to get, you have to allocate the largest possible page table for every process to allow it to grow to the maximum possible value. Okay. So, this might mean a lot of wasted space if most processes are going to stay small. You just allocated a giant page table thinking that maybe the process will grow. That is going to waste memory because the page table has to be stored in RAM. Right. So, what do? Okay, you make the page table 2 levels. You essentially say that I have a 2 level page table and the first level is going to be also fixed, but it is smaller, and then as the process grows you essentially add a second level of index. Right. So, and then you can allocate these things are allocated on the fly, and then depending on how large the process goes, the second level entries grow only as the process grows. The first level is pre-allocated. These things can be dynamically allocated. Okay. So, that is a multi-level page table. It requires 2 levels of lookup. You have to go to page table 1, level 1 to figure out which of these second level entries to go to. You go there, that tells you the frame number. Where have you seen this data structure before in an OS class? Probably seen it in a database class as well if you took a database class. In a database course, it is a binary tree. A B tree actually uses multi-level. Okay, but you have seen it if you taken an OS class, you have probably seen it elsewhere, where the exact same argument holds as to why it is a multi-level index. This is called a multi-level index incidentally, it is just a 2, in this case 2 level, it could be k levels. Yes.
File system.
Okay, used it in a file system. inodes in a file system also use the same multi-level structure for exactly the same reason. Because when you create a file, the OS or the file system does not know how large the file is going to be. Okay. The index node is essentially exactly the same mapping that maps block numbers to locations on disk. Okay. And the only way you are going to keep it efficient is to have a small data structure which is called the inode, and then have a multi-level index that grows as much as you need to, rather than creating a gigantic index for every file. Right. Exactly the same concept holds even for memory allocation. So, more sophisticated processors will support multi-level index. Okay. And then you will see in this case you will have your address will have two pointers, pointer to page table level 1 and level 2, then an offset. Okay. So, that is something you want to keep in mind. Okay. So, let us move on to, I am going to skip the TLB and go to segmentation. Okay. So, let us take a little look at how hardware supports segmentation, so that you get a better feel for how Minix has to implement segmentation. Okay. So, I said that every process has at least 3 segments, okay, which is stack, heap and text. Okay. But typically processes will have more than 3 segments, they can have many segments. Okay. What is shown in this picture. Okay. This picture shows an extreme case where every data structure that you allocate for the process is its own segment. Okay. You want to create a large array, make it its own segment. You want to create like maybe you want to create a hash table, let us make it its own segment and so on. Okay. So, what this does is now each of these, you will see that is the stack, that is the text, but you will see that there is a tree that the data structure that they allocated, they made it its own segment, and there is a symbol table its own segment. The good part about doing this is each segment can grow independently of others. Okay, so, if you want to grow the particular segment, that segment can grow and other segments can stay the same. So, that allows us some flexibility, because we stored each segment independently, that contiguous region. Each segment can grow or shrink based on the needs of that process. Text segment never changes incidentally, text segment stays static, but the heap can grow, stack can grow, and if there are data structures, the heap that are stored as separate segments, they can grow and so on and so forth. Okay. So, that gives us that flexibility. So, depending on how much flexibility you want, you can actually have multiple segments in a process typically. Okay. Shared libraries are also their own segments. Okay. And you can not only have shared libraries, as we will see soon, the entire text segment can also be shared. Okay. So, there will be multiple shared segments which allows us to do this granular sharing across processes. Okay. Now, there are many advantages and disadvantages of using paging as a memory management scheme, using segmentation. We talked about this last time. Excuse me. So, I am going to quickly talk about this here. So, you will see that excuse me, if you have these tables or data structures, it is much easier to change their size if you are using segmentation than paging, because paging has no concept of what is in the page. So, process is a collection of pages. Okay. The OS does not know what is in the page, does it have code or data. Okay. But segments essentially have a purpose, either it has code or it has data. There are only two kinds of segments. Okay. So, you can essentially say this segment can grow because it is a data segment. The other thing you can do is in the text segment, you can make it read only, because code once you load for a process does not change. So, typically text segments are made read only. Okay. That is also a security measure, by the way, because if you make the code segment writable, you are now vulnerable to things like code injection attacks, and your hackers can essentially take over your process and inject code and start executing it. So, you do not want that to happen. So, code segment typically made read only. Okay. Data segments like stack and heap are read write. So, you can write to them because you can change values of data that are stored in there and so on. But data segments are also set to no execute. That means that you can never fetch something from a data segment and execute it on a processor. Okay. For the same reason, okay, because that is a security vulnerability. If I could actually inject some code into an array and tell the processor saying go to that location and execute that code, that allows you to take over a process, inject malicious code and execute. Okay. So, typically data segment is set to no execute. Okay. There is hardware support to do this. There is something called an NX bit on Intel processors, which essentially stands for no execute. Okay. That allows you to mark all the data segments as no execute, because it became such a big problem that they introduced hardware features to do this. So, typically if you have segment level, you can do this. Entire segments can be marked as read only, so you can't change it. Entire segments can be marked as no execute, so you can't execute anything in there, just read or write to it and so on and so on. Okay. All of that comes with segmentation. It's harder to do in paging, because you need to then assign semantic knowledge of what is in a page. You can also make pages read only or no execute, but you need to know what is in there. By definition, you know what is in a segment because you created that segment for a purpose. So, you can assign meaning to it and have all these additional features assigned to it. Okay. So, that is all I am going to say here, and then move on to segmentation. Okay. So, here is what I am going to show in this slide and the next slide is the picture of how Intel x86 processors have support for segments. I talked a little bit about paging, and let me now talk a little bit about segmentation. What they should tell you is Intel processors allow you to do both segmentation and paging. So, it is very easy to do segmented paging. Okay. You have a question? Yes.
You mentioned that segments can grow and shrink independently, but that will also depend on the size of holes in between, what extent they can. So, there will be a limit, right?
Yes. So, question is, I did say segments can grow and shrink, and that will depend on how much holes you have between two segments, and there will be a limit to that, certainly. So, this goes back to how you allocate segments. So, if you actually assign two segments very close to one another, one of them is a data segment and it grows, it will be limited by how much it can grow. So, there are only two things you can do at that point, either give an error saying out of memory, because if you do malloc, eventually you will get an error, or you got to move that segment to a bigger hole, which involves memory copying. Right. So, both of that is extra work or causes inconvenience. So, doing this well when you allocate segments to virtual memory regions is actually a smart thing to do. So, you want to leave enough of a gap in segments to allow you to grow segments, specifically data segment. Okay.
How do you know what is good enough gap based upon history?
Okay. So, how do you know what is a good enough gap? That could be a parameter that the OS designer picks, for example. Or you could say every process at least gets a hole of a certain size. Okay. Because typically the heap, or not the heap, the stack will be very small when the process starts. So, you cannot give it a 10 byte chunk and assume that it will be done. So, you will actually allocate a hole that is much bigger, and so that it can grow. So, that all of those are design decisions as to how large you make a stack by default and things of that sort of heap. Okay. Any other questions? Okay. So, let us talk a little bit about segmentation. So, as far as Intel processors are concerned, there are two tables that are kept in hardware. There is something called the local descriptor table and there is a global descriptor table. Okay. They do not call them page, not page, they do not call them segment tables, but they are essentially the segment table is called the descriptor table in Intel architecture lingo. Okay, so, this is a name for segment tables, but they call it descriptor. So, essentially the global descriptor table is one for the entire system. Every process has its own local descriptor, say a segment table. Okay, and then there is one that is system wide, that is meant for the OS and system segments and so on. Okay. Now, how does all this work? So, here is a picture. It looks fairly complicated, but it is really not. So, that is an entry in the segment table. Okay. Essentially, the only two things here that are really of we care about is where does that segment start in virtual address space and what is the size. Okay, those are the base and limit register. Okay. So, what you are going to do is you are going to use this selector entry saying which segment do I care about, because there are multiple segments for the process. So, if you need the fifth one, you are going to that entry will have 5, and then you are going to essentially that is going to be a table of several entries. So, you are going to look at the fifth one and then extract the base and limit register. Okay, and then once you do that, you have this hardware that is going to allow us to find a actual address. So, here is our you have virtual address. You take the virtual address and say which segment is it in, you get the segment ID, look up the right segment entry, that gives us the base address, you take the base address and the offset, and that gives us a 32-bit address on a 32-bit machine. Are we done with this translation? Okay, remember this is segmented paging, and I showed you a more general picture last time. It said segmented paging has 2 levels of translation. This has simply given us an address, but that is an address in virtual memory. We have not done any page table lookups here. Okay. So, you will take that address and then you will do another level of translation, which we already looked at, which is this, because you are going to take that address, find the page number, and then actually find a physical address. That was essentially trying to figure out relative to based on a relative offset in a segment, what address do you have in the virtual address space. Then you take that virtual address space and say which page in my RAM do I need, and that requires us to go through the MMU logic to do a second level of translation. Okay. So, that is something you want to keep in mind. This is just given us a 32-bit linear address, and here is what you have to do the next level of, depending on whether it is a multi-level page table, you are going to take that address and essentially find a physical address. Okay. The good part is all of this is done in hardware. The OS is not really doing much, okay, other than executing a program that just generated an address, and all of this is actually happening under the hood. Okay. That is our Intel architecture. That is what x86 does for us. Okay. Something you want to keep in mind, because when you look at the code, you will see all of these things going on, and you need to know this is what is happening under the hood. Is this clear? Any questions here? This is obviously not Minix specific. This is x86 or Intel specific. Okay, but Minix is going to use it to implement its segmented paging approach. Okay. So, with that in mind, I am going to show you a little more of the process manager, and we will see some things in there that are specific to memory management. Okay. So, here are some of the system calls that are implemented in the process manager. We already looked a little bit at fork and exec, which is here, okay, which are going to allocate memory for us. Okay. So, that is the part of the process manager that is intimately tied with memory allocation. Okay, I am going to skip, and there are lots of others that I am going to skip for now. Okay, you will see that there is another one here to allocate memory and free memory. So, you can use that to do things like malloc, which allocate memory on a heap. Okay. Fork and exec allocate memory for a process. User processes, when they try to dynamically allocate memory, you go back to the process manager, which then talks to the memory manager and allocates more memory on the heap in this case. Okay. Now, this is a picture that shows us an example of sharing entire text segments. So, you will see here there are two processes. That is the segment table for process 1, there is a segment table for process 2. Forget all the hex numbers here, that is not important. Only thing that is important is you see that the text segment for both of these processes are pointing to the same segment in virtual address space. So, there is one segment there. Okay. The heap and the stack are separate. So, you will see that there is a separate stack and there is a separate heap for each of these processes. Okay. So, you could ask, why do I need to share a text segment across two processes? When will this actually happen? Yes. Okay, if you run two of the same process, you start two terminals, you start two of your busy programs. Well, I forget what it was called for lab 2. Right? If you start multiple copies of the same process, okay, why should the OS load those twice? It is going to essentially have only one copy and then share that text segment across processes. In this case, the text segment, remember, is read only, it does not change. So, it is perfectly safe to share it. Okay. Same is true of shared libraries. Okay. If two processes that are different, but they still use the same library, you will load one copy of the library and the library segment will be shared. Okay. So, this allows us to make more efficient use, not have redundant copies and so on. And furthermore, in this case, the text segment can also be stored on the file system, as we talked about. It does not actually have to be on the swap partition. That is an even additional optimization. So, there are quite a few optimizations that are used to make efficient use of virtual space, memory and so on. Yes, question.
This makes it seem like in my mind that there's one virtual address space, but each of these processes have their own virtual address space, and they share both the segments and the page table entry for that shared segment?
Yes. So, the question you are asking is there one virtual address space or multiple address spaces? Is that your question? Okay. So, there is one swap space. Okay. When I say virtual address space in this lecture, I actually mean that swap space. So, this could be a 10 GB disk partition. So, that is our virtual address space. It will start from 0 and go all the way to 10 GB in size. Okay. So, let us assume that is one large array. Okay. That is shared across processes because there are multiple processes running. Each of them is using some part of that disk. Okay. So, in that sense, that virtual address space is shared. Now, we also use the term virtual address space to mean relative addresses for that process. Okay. So, each process has its own logical view that is independent of virtual memory, that is this view, saying that I am a process of size n, my addresses go from 0 to n, here is my text segment, here is my heap that grows up, here is a stack that grows down. So, each process thinks its memory looks like this. Okay. So, it generates virtual addresses, but those virtual addresses are relative to this virtual address. So, we use that the term virtual in an overloaded manner. That is the virtual address space of a process, which is just the memory it can see. That is the virtual memory, okay, which is not the same as the virtual address space of that process. That just says that is the swap partition on disk from which I am paging. So, there are virtual addresses that go from 0 through n, that is the disk partition. This is the virtual addresses or relative addresses of the process. So, slightly different things. The term has been somehow misused in the way we have been using it and the way it has been used, because they are actually two distinct concepts. The reason they call it virtual is essentially it is distinct from physical. That is why it is called virtual really. Okay. But virtual memory is not the same as the virtual address space that a process sees. Yeah. So, these are addresses in virtual memory, these are addresses in the virtual address space of a process. Is that clear? Okay. All right. So, this is about segment sharing text segments and whatnot. Okay. Now, if you look at the code again, you will see that there is a structure that is used to track holes, that is called the hole list, the list of holes. So, that is what you are going to scan to allocate memory for a new segment, or if a process completes, you are going to take that segment, maybe merge it with the adjacent holes, make a bigger hole and reinsert it and things of that sort. Okay. So, that is the data structure you have to manipulate to essentially allocate and deallocate memory from virtual memory in this case. Okay, because physical memory is paged, so that is not being used contiguously. Okay. So, again When we talked about fork, I mentioned some of this, but I just want to put the steps of fork once again, and you will see that there are essentially, when you look at fork, you will see that there is essentially some memory management that is going on here, which you allocate memory for a child process, then you essentially enter that memory map into the process table and so on. Okay, so fork and exec are the two parts of the process manager that make very closely integrated with how memory is allocated to processes. Okay, so that's something you want to keep in mind. I won't go back to what fork does. We already talked about that. This was just to remind you that there's memory management that's implemented as part of fork. Okay, same is true of exec, okay, which I will not go into detail here. All right. So there are several other system calls in process management which you should know about, but I am not going to cover them in any detail. There are some that allows you to essentially do time and so on. Okay. Maybe you are going to use some of this for your lab when you try to figure out the turnaround times and so on. But you use library functions, but those library functions essentially call some of these functions to figure out. This is doing process accounting. How long did the process run? When did this start and so on. Okay. There are several others that allow you to get IDs of processes, groups of processes and so on, or change process groups, which in this class probably you are not going to encounter much, but you should know they are there. Okay. And then there are of course calls that the process manager implements to allocate memory and whatnot, and there is some to do debugging. Okay. So these are the three calls that are the most important. Okay. Allocate memory allocates a block of memory, free memory frees it, and initialize memory tries to initialize the free list. Okay. There are some other calls that some OSs support, and I do not really know if Minix does it, which says when you allocate a memory you should zero out its contents. Okay. That is done for security reasons. Maybe I am a process, I put some sensitive data in my memory, okay, I allocated some memory and I freed it. If it just goes back to the free list and gets allocated to some other process, it reads it, it can find some other process's data. So typically when you want to allocate new memory, it's a good idea to zero it out. Some libraries do that and some don't. Okay. But that is something that is an important consideration as well. If you want to keep things secure, you want to zero things out, or at least rewrite it with random bits, so that other processes cannot see what was in that memory region that was put in there by a previous process. Okay. All things to keep in mind when you implement an OS. So let me now take a few minutes, okay, we have a few minutes left, to show you some code in Minix. Okay. So this is the Minix GitHub. I am going to first go to an older version. Okay. So let us take 3.1. Okay. So this is an older version of Minix, and here if you go into servers, okay, you will see that there is no memory manager. Everything is in the process manager. There is no VM directory here. Okay. So this is a process manager, and you will see again here, if you go to alloc.c, make this a little bigger. So you will see it says it is concerned with allocating, freeing arbitrary size of blocks in physical memory. So in this case in 3.1 there was no virtual memory, there was no paging. You assume that entire processes were always present in RAM, and they were essentially allocated as a collection of segments, which means that this picture that you see in virtual memory was what physical memory looked like. Okay. So you will see here code to essentially do equivalent of, so you will see that there are holes, and then you can essentially, you see this notion of a click that I was mentioning, because they have this abstract term called a click, which looks like a page. Essentially in this case it was 1 kilobyte, now it is 4 kilobytes, and then you will see that there is code to look for. So here is free memory, and then here is where did allocate go? Okay, so mem init. Okay, so I think I passed it. Okay, so here is allocate memory. So this is what is going to implement something like first fit or best fit or some any policy that you want by scanning the list of holes and whatnot. Okay. So, I think just as an exercise, even though this is an old version of Minix that we do not touch in this class, you should just go to that version and just take a look at the code, so that you get some feel for how things were in a simpler version of Minix. Okay. Now, what we have in this class is this one 3.2.1. Okay, and you will see here, if you go to servers, you will see that now there is a process manager and that's your process manager, but now your memory manager is now in the VM, the virtual memory manager. Okay. So, all of what was in the process manager alloc.c has moved here. Okay. And now you will see that there is stuff, you will see page faults.c, because now you have to deal with paging and demand paging. So, you have to deal with page faults and whatnot. So, the code has changed substantially between 3.1 and 3.2, because they started introducing support for new hardware. Okay. This is what we will use in this in the lab for this course, but it is good to see and compare. Okay. What has changed and so on. I mean, not a lot of code, but you get a good feel for how you can write a very simple OS that does very simple memory management, and how do you write a more modern one that uses segmented paging and things of that sort. Okay. The other thing I will mention here is you will see that there is a directory called arc, that is the architecture dependent code. Okay. And you will see here, if you go in here, there is a Intel and there is ARM. The ARM one is empty. So, it looks like as of 3.2 at least, support for ARM was not implemented, but x86 you will see that there is plenty of stuff here. So, you will see that the page table.c is here, because that is dependent on the architecture, because Intel processors have a certain type of page table support. So, all of that is implemented here. Okay. So, you will, and then if you can go to even more recent version, which is 3.3. Let me go back here. Okay, so that is 3.3. So, that is the newest version. Okay, the code has changed even further here. So, you got to go into Minix, and then you got to go into servers, and you have now virtual memory manager, you have arc. Okay, I guess they did not implement it. I thought that they had a support for ARMs, but there is not one. But yeah, so that I think there is some beta version, but there is some code, it is not in here. But in any case, if you have support for new processors, that is where you put it, and all the architecture independent code is in the virtual memory manager directory. Okay. So, that is the general lay of the land as far as Minix memory management is concerned. We have a couple of minutes. Are there any questions on any of this? Okay. Lot of this is tied to both the hardware and what memory management scheme is actually used. And the modern and Minix, current Minix looks as modern as any other OS. It does paging and segmentation and things of that sort. It complicates things quite a bit. So, if you look at 3.1, things are very simple. In 6 files or so, you implement all of memory management. Now, it is quite complicated. Yes.
How does the OS know which architecture is there?
How does the OS know which architecture is there? So, this is defined at compilation time. So, when you compile your kernel, typically you set the architecture type in the make file. So, the binary that is created pulls the right architecture files and only compiles support for that architecture. So, if you compile your Minix kernel, in this case by default it is set to compile for x86, it is not right. So, the OS does not actually need to know, because the kernel is designed, the binary is designed to run on one architecture alone. The code might have support for multiple platforms, but when you compile it, it is basically compiled for one platform. Okay. If you Linux kernel, which I am not sure that the Docker lab will, one of the things you set in the make file is what architecture you want support for, and then it basically pulls together all the architecture specific, and then you get architecture specific version of the kernel. Okay. All right. So, we are going to stop here today, continue next time.